Hello everyone, this is Dilip. In today's video, let's talk about solving the logistic regression using gradient descent. So in the last video, we have seen transforming our hypothesis function into a sigmoid function, which has helped us get our hypothesis to be a value between 0 and 1. And this hypothesis value indicates the probability that our given variables belong to a particular class. So remember, this is a binary classification problem. So the hypothesis will indicate that our given variables belong to a particular class. What is the probability of that? And we have already plotted the sigmoid function, how it looks like for a given z. And this is our transformed hypothesis. Okay. So for linear regression, it is just theta transpose x. For logistic regression, it is 1 by 1 plus e to the power of minus theta transpose x. So this is the cost function we used during linear regression. And this is a mean square error cost function. So if we apply the same mean square error cost function with our hypothesis, with our new hypothesis, which we are using for logistic regression, which is 1 by 1 plus e to the power minus theta transpose x, what we get is, if we plot this cost function, a non-convex function, which looks like this. So here you can see there are many local optimums. So there is one local optimum here. There is one local optimum here. There is not a single global optimum. So if we apply gradient descent using this cost function, then what we'll end up is, we'll end up somewhere in the local optimums, but there is no guarantee that we will end up in the global optimum. Now, to resolve this problem, what we need to do is, we need to convert the cost function such that our hypothesis can fit in appropriately. Modifying the cost function to fit our hypothesis, we get a cost function like this. So how this cost function is derived, it will be advanced statistics, which I'll not go in the today's video. But as you can see, this cost function, if you take in y-axis and you take theta in x-axis, and if you plot the cost function, you will get a nice function like this. Which is a convex graph, and you can see it has a global optimum. Now you can apply gradient descent on this graph, because you know you will end up in a global optimum no matter what. There are no other local optimums. Moving on. So similar to linear regression, the formula is same. So repeat until convergence. Simultaneously update the theta parameters such that you subtract from the current iteration theta to the previous iteration values of theta, putting them into this derivation. So this is simply nothing but subtracting the gradient. That's what gradient descent is. So you take initial theta and you keep on iterating, and getting the values of new values of theta such that these both values converge both on the left hand side and right hand side, and this should become very minimal, the slope value. And what you can see, one more thing is, this looks, the derivation of our cost function looks exactly same as a linear regression derivation of cost function, because it also looks the same way. But remember, earlier our hypothesis is theta transpose x, but for logistic regression our hypothesis is 1 by 1 plus e to the power minus theta transpose x. So fitting this into this, you can see this derivation is not exactly same as logistic regression, but it looks the same way. And one more thing is, instead of individually writing each of these lines when you are coding, what you can do is you can take the theta parameters in a vector and use vector subtraction for getting all the values of theta in one single subtraction, such that code will be reduced and it will be in much more readable format. So that's it for today's video. What you have seen in the end is the most widely used machine learning algorithm, which is using gradient descent to solve logistic regression. Thanks everyone for watching the video.